This paper, titled Text-to-TrajVis, Enabling Trajectory Data Visualizations from Natural Language Questions, is authored by Tien Bai and colleagues from institutions like Jilin University, Macau University of Science and Technology, and WeBank AI. It introduces a new approach to make it easier for people to visualize trajectory data using everyday language. Trajectory data refers to information about the paths that objects, like vehicles or people, take over time. This data is increasingly common from sources such as the GeoLife Plus dataset, which tracks human movements, the T-Drive dataset from taxi trips in Beijing, and the World Trace dataset for global tracking. Researchers use this data to study things like human mobility patterns, how diseases spread, or even animal migrations. For example, it helps in analyzing traffic flows or predicting the spread of infections based on movement. The challenge is that current tools for querying and visualizing this data often require specialized knowledge, like programming or understanding complex software. This makes it hard for non-experts, such as urban planners or everyday users, to gain insights from it. To solve this, the paper proposes a technology called Natural Language to Visualization, or NL2VIS, specifically adapted for trajectory data. They call their version Text-to-TrajVis. In Text-to-TrajVis, users can ask questions in natural language, like, "Show me the trajectories of taxis in Beijing during rush hour," and the system automatically turns that into a visual representation, such as a map. The process involves parsing the question to extract key details like location, time, and other parameters. Then, it converts this into a custom language they created, called Trajectory Visualization Language, or TVL. TVL is designed to specify queries for trajectory data and generate visualizations, like maps or charts. For instance, if someone says, "Visualize the paths of vehicles in New York City from 8 a.m. to 10 a.m., the system would break it down, identify the area and time, generate the appropriate TVL code, and produce a map showing those trajectories. Since this is a new task, there wasn't any existing dataset to test or train systems on. So, the authors built one from scratch. They started by developing TVL as a structured language. To create a dataset, they used a combination of large language models, like GPT or Llama, and human input to ensure high quality. The process had two main stages. First, they created a base set of TVL examples by using templates that included geographical and temporal elements. For example, they might start with a simple TVL template for plotting trajectories in a specific area and time. Then, they expanded this by adding various constraints, like speed limits or specific types of vehicles, organized in a tree structure. This way, they generated a wide variety of TVL statements. Next, they used large language models to pair each TVL with corresponding natural language questions. For example, for a TVL that queries trajectories in a city during a certain period, the LLM might generate questions like, "What are the movement patterns in downtown during peak hours?" This collaborative approach, combining AI generation with human verification, resulted in a new dataset called TrajVL. It contains over 18,140 pairs of natural language questions and their matching TVL codes. To test how well this works, the researchers evaluated several large language models, including GPT, Qwen, and Llama, using the TrajVL dataset. They measured how accurately these models could translate natural language questions into correct TVL outputs. The results showed that while the task is feasible, meaning models can handle it to some extent, it's also highly challenging. Models often struggled with the nuances of spatial and temporal details, like correctly interpreting ambiguous locations or complex time ranges. This highlights the need for further improvements in how language models handle visualization tasks, especially for specialized data like trajectories. The paper points out that large language models are powerful because of their ability to generalize from examples. In this case, they used a technique called Retrieval Augmented Generation, or RAG, where the models retrieve relevant information from a knowledge base to improve their responses. Overall, by introducing Text-to-TrajVis and the TrajVL dataset, this work opens up new possibilities for making trajectory data more accessible. It could lead to better interfaces for applications in fields like transportation, public health, and environmental monitoring. For example, City officials could use simple voice commands to visualize traffic patterns in real time, without needing data experts. The authors emphasize that this is just the beginning, as the task involves not only language understanding but also domain-specific knowledge about trajectories. They encourage the research community to build on this by refining models and expanding the dataset. In terms of methodology, the paper describes a systematic way to generate TVL. They started with seed examples and then systematically added constraints based on a tree structure. Each leaf in the tree represents a specific query aspect, like filtering by speed or direction, which allows for a rich and diverse set of examples. The experiments also revealed interesting insights. For instance, while models like GPT performed well on straightforward queries, they faltered with more complex ones involving multiple constraints. This suggests that future work might need to focus on fine-tuning models with more trajectory-specific training data. Finally, the paper notes that this integration of natural language processing with visualization has broad implications. It could extend to other types of data beyond trajectories, making data analysis more inclusive for non-experts. By benchmarking LLMs on TrajVis, they provided a solid foundation for ongoing research in this area.